You give an AI agent a 12-hour task. It runs, fills its memory, summarizes what it did, and keeps going. Hours later, you check the output. Half the features are broken, some are missing entirely, and the agent thought it was done. To understand why, go back to 2022. ChatGPT launches with a 4,000 token context window. That is the entire working memory. Developers immediately ask, how do you get serious work done inside such a tight space? The first answer was prompt engineering. Craft your instructions carefully, define the agent's persona and identity, and steer the output through text alone. It worked for simple tasks, but the moment complexity increased, it hit a ceiling. So, developers moved to context engineering. Three techniques emerged: tool calling, which let agents read only the relevant files from a repository instead of loading everything; MCP, the Model Context Protocol, which exposed vendor-specific capabilities on top of the base model; and RAG, Retrieval Augmented Generation, which connected external databases so the agent could pull in the right data on demand. Early coding agents, Cursor, Ada, Claude, adopted these patterns and got strong results. But a new problem surfaced on long-running tasks. Ask an agent to work for 12 hours and the context window will fill up. The only option is to summarize, compress everything the agent did into a shorter record and continue. That summarization is lossy. The agent assumes features are finished when they are not. It glosses over failures. It loses track of what was actually verified. The concrete result: ask an agent to clone an entire website and you get something that resembles a website, partially. Placeholders where images should be, incomplete logic, untested code paths, and a confident agent that considers the task complete. The industry experimented with alternatives: sub-agents, hierarchical structures where one agent delegates to others with their own context windows; agent swarms, pools of parallel agents, each holding a slice of the problem. These experiments were messy, but they pointed at something important. Better orchestration, better execution, isolation, and cleaner context management were the real levers. In early 2026, the term agent harness engineering was coined to name this shift. It was not a brand new invention. Developers had been building toward it for years, but the term captured a genuine paradigm change in how AI agents are structured and run. The core change is the loop. Instead of one continuous execution where the agent runs until its context fills up and then summarizes, the harness steps back one level and controls the loop itself. Each iteration begins with a fresh, clean context window. The agent operates under strict rules for how to start and how to finish. When one iteration ends, the harness feeds the relevant state into the next, not through summarization, but through structured handoff. The results are dramatically more reliable. Roo is a clear example of this in practice. Its architecture is almost surprisingly simple. Generate a requirements file up front, loop through each task, select one task per iteration, execute and test it, document the outcome, then move to the next. 5 steps. Repeat until done. Anthropic's own harness demonstrations follow a similar pattern: lightweight, minimal, and effective. Harness engineering does not replace what came before. Prompt engineering still defines the agent's persona and its behavioral rules. Context engineering still manages what information the agent sees inside each iteration. Harness engineering sits above both. It is the orchestration layer that decides when to start a new loop, what state to carry forward, and how to structure the workflow from requirements through implementation to testing. The reason agent harness spread quickly through the industry is not hype. It is because it demonstrably works. Reliability goes up, task completion rates improve. The pattern is simple enough to implement in many different ways, which is why you see it across so many modern coding agents, each with its own variation. The interesting open question now is how far the loop paradigm scales and whether the same architecture that handles a 5-step coding task can hold together something far more complex.